Hello students, welcome. This is a question of rod sliding on the rails under the chapter Electromagnetic Induction. In this question, the specialty is that there is a capacitor connected here, uncharged capacitor, and a battery is connected. Let us see how we can find out the velocity of this rod. So before we start, I will request that please subscribe to my channel and like the video also, and please leave your comments after seeing the full video. Thank you. So here the question statement: a conducting rod Mn, this is the rod Mn of Mn is the name of this rod, okay, of mass M and length L. Mass of the rod is M, length is L, is placed on parallel smooth conducting rails connected to an uncharged capacitor of capacitance C and a battery of EMF E as shown. A uniform magnetic field B is existing perpendicular to the plane of the rails. So basically in this arrangement, you know that the rails are in the horizontal plane and the rod also moving in the horizontal plane, and the magnetic field is vertically downwards. So the steady state velocity means constant velocity acquired by the conducting rod Mn after closing the switch S is, so right now the switch is open condition, so after the switch will be closed, this battery will supply current into the circuit and then rod will begin to move. So neglect the resistance of the rails and the conducting rod. Here are the four options. Okay, what students we can do, you can pause here and try to solve the question by yourself to see which option you are getting, or after that you please proceed and see how I solve the problem. So let us start to analyze our problem. What happens when you close the switch? After closing the switch, the battery E, this battery of EMF E, begins to supply current I and the capacitor begins to get charged. We know that a battery supplies current from its positive terminal. So from the positive terminal, current begins to go out and it will travel along this, and this rod is creating a closed circuit between the battery and the capacitor, okay? So the current begins to flow clockwise, and you know that current cannot flow between the plates of capacitor. So basically this current is delivering charge through the rod into this lower plate of the capacitor. So lower plate of capacitor will get positive charge plus Q, because current is the flow of positive charges. So positive charges will come and get deposited on the lower plate, and from here what is happening to upper plate? This battery is sucking the charges from the upper plate, taking away charges from this plate. So therefore, due to the deficiency of charges, this plate will become negative charge. So charge is being taken from this plate by this battery and being delivered through this rod into the lower plate. So lower plate is positive. Then what happens next? The current will be related to the charge in the capacitor as I is equal to dq by dt, because charges are flowing in this circuit and the rate at which the charges are depositing in the capacitor is equal to the current in the circuit. Now due to the flow of the current in the rod, now you see the current is flowing through the rod, it's a conducting rod. The rod will experience a force ILB towards right. Why it will experience a force? Because in magnetism you might have studied that a current carrying conductor experiences a force in the magnetic field. So there is a magnetic field B over here, and current is flowing in the rod, so the rod will experience a force ILB. Why does the rod experience a force ILB to the right side? Why not to the left direction? For this, we have the Fleming's left hand rule. So on the left hand, the first finger is representing the direction of magnetic field. So what you do right now, you take your left hand and point your first finger into the screen. As the magnetic field is going into the screen, and this finger, the second finger, is toward the direction of current. So current is going down. So you adjust your fingers in such a way that the first finger is going into the screen and the second finger is downward direction along the current direction. So you will see that your thumb is coming to the rightward direction. That gives the direction of the force. So using the Fleming's left hand rule, you can find out that the force acting on the rod is rightward direction. Now what will happen due to this force? Due to the force, the rod gets accelerated and hence its speed increases. So firstly, because of the force, the rod is going to get an acceleration, and this acceleration will give velocity to the rod, and the velocity will keep on increasing because acceleration causes the increase in the velocity. Now comes the electromagnetic induction. Due to the motion of the rod, a motional EMF E dash is equal to VBL will develop in the rod. So we can replace the moving rod with a battery whose EMF is equal to VBL, the motional EMF developed due to the motion of the rod. And the polarity of the rod can be seen to be like this: upper end will be positive and lower end will be negative. Okay, let us continue to the next page now. So now what happens? So force is getting applied on the rod. So note that the battery E, this battery which is already present in the circuit, causes clockwise current. Okay, so it is sending current in the clockwise direction. Even in this circuit also we are showing it is giving clockwise current. And the induced EMF E dash, this one, because its positive terminal is on the upper side and current will be going out of the positive terminal like this. The current is anti-clockwise current. So the battery already present in circuit is going to develop a clockwise current, but the induced EMF is going to develop anti-clockwise current. So both of them are opposing each other. Now in this graph I am showing something, explaining something here. See, so what is happening that in the beginning the induced EMF E dash is smaller than the battery EMF E. In the beginning, actually, when the velocity of rod was 0, then this EMF E dash was also 0. V is equal to 0 means E dash 0. But as the velocity increases, the EMF E dash also increases. So I am showing that in the graph that the induced EMF is increasing. And but battery EMF, always remains constant. So the battery EMF is constant. So what happens after some time, as the induced EMF is increasing, it will reach a value equal to the EMF of the cell after some time. So as the rod gains velocity, the induced EMF E dash keeps on increasing because velocity increases, so induced EMF increases. So after some time, the induced EMF becomes equal to the EMF of the cell. So this graph you see, the induced EMF becomes equal to the EMF of cell. So what happens? Both of them are opposing each other. So ultimately, the net EMF of circuit will become 0. E minus E dash will become 0. So at this moment, the current in the circuit becomes 0. Yes, because both of them are sending same amount of current, both are opposing each other. When both the EMF become equal, so after this moment, the net EMF of the circuit becomes 0, and so the current in the circuit also becomes 0. So let's see what happens next. So as the current in the circuit becomes 0, the force ILB also becomes 0. See here, the force depends on the current. F is equal to ILB. So when the current becomes 0, the force also becomes 0. And if the force becomes 0, hence the acceleration becomes 0, because acceleration is force upon mass. So acceleration of the rod becomes 0. And we know from kinematics that when acceleration becomes 0, then velocity becomes constant. So the velocity becomes constant. And we call this constant velocity as a terminal velocity. Look at the graph on this right side. So in the beginning, the velocity of the rod was 0, and now the velocity is increasing. But the moment acceleration becomes 0, the velocity after that moment becomes constant. So after this moment, the velocity becomes constant, and thereafter the velocity will remain the same value even after a long time. That constant velocity is the Vmax, or the terminal velocity here. Okay. After that, velocity no more increases. So we will say that moment the velocity is maximum velocity. Now, as the current has stopped, charging of the capacitor also stopped, because in the beginning, as I said, the current which was going here was delivering charge into the capacitor. But as the current has become 0, so charge delivering to the capacitor will also become 0. But by that time, the charge already filled in the capacitor. You see, from beginning, the charge was already getting filled in the capacitor. And so after this moment, no more charge goes into the capacitor. So whatever charge was filled up till now, that becomes the maximum charge, the Qmax in this capacitor. So we'll say that hence the charge also attains a steady constant value, which we call Qmax. Next, let us now solve the question. Apply Newton's law on the rod. Okay, but not now. Long before it acquired terminal velocity. As I just now said that after some time current will become 0, force will become 0. But before that time, when the force was not 0, current was not 0, then at that moment let us write down our equation of Newton's law. So F is equal to ma. Net force is equal to mass into acceleration. The force is ILB on the rod. Current I can be written as dq by dt and acceleration dv by dt. See, I am talking about the moment long time before attaining the terminal velocity. Okay, so at that time the velocity was changing with time, so therefore acceleration dv by dt. Even the current was also increasing at that time, so I dq by dt. Now what to do next? Cancelling dt from both sides. You cancel the dt both, cancel, and remaining thing is just dq into lb is equal to m into dv. Now we can integrate on both sides. Integrating on both sides we will get, so put the integration symbol. See here L and B both are constant, length of the rod and the magnetic field B is constant, and integrate this dq. And on the right side mass of the rod is constant, integrate the dv. Now the lower limit of integration represents the initial values. So you know, in the initial time when the switch was closed here, then at that time the charge in the capacitor was 0. So the initial value of charge was 0. And the rod also had initial velocity 0. And after some time, as I said in the previous page in the graph, charge will reach its maximum value and velocity will also reach its maximum terminal value. So that is the upper limit, means the final values. So after solving this, we will get this expression, and by simplifying this, the value Q max will be mV max upon LV. Now let us come to this circuit. See, when we solve the problem of electromagnetic induction, so you should apply the Newton's law on the rod and get one answer, and then you should apply on the equivalent circuit, you should apply the Kirchhoff voltage law, KVL. So applying KVL at any time t, we can write down so let us traverse the circuit clockwise direction, okay, like this. Let's learn how to apply KVL in a circuit. When you apply KVL in a circuit, you may choose either clockwise direction or anti-clockwise direction. I will choose clockwise. I will start from here. From this point I will go like this and like this, and I will end here. So as I move up, the voltage of this battery is E. I write down E here with a plus sign here, not minus, because as I move from the lower potential to the higher potential side, you see, longer line means higher potential, smaller line means lower potential. So lower potential to higher potential, the value potential increasing, so increase will be written as plus E. But as I move here clockwise and I traverse along this direction, I am going from plus positive terminal to the negative terminal, so potential decreasing. So decreasing represented by minus sign, value is VBL. So plus E minus VBL, and then same law applies to capacitor also. As I move from here positive to negative terminal of the capacitor, so plus charge to minus charge, potential decreases because positive plate has higher potential, negative plate has lower potential, and I am moving clockwise like this. So if you go clockwise, you will write down minus Q by C. So actually I have already brought it on the left side. So minus Q by C equal to 0. So actually the equation should be E minus VBL minus Q by C equal to 0. So minus Q by C I sent to the right side of the equation. Continuation. Now this is the KVL at any time t, but after long time, when the charge becomes Q max and velocity becomes V max, then this equation will become, after the steady state is reached, velocity become V max, charge become Q max. Other things are constants. Now you substitute the value Q max over here. So we will get this 1 by C taken side and Q max value substituted here. So the same equation written here. Now send it to the right side. This term also containing V max, here also V max. So you send it to the right side and take V max common. Send it to this side, take V max common. We get this in the bracket. Now we'll simplify this. We'll get this, and finally here is the answer. So this is the answer of the question. You check Did you check in the beginning? Did you try it by yourself? And you see, this is the answer that we are getting. So I think the option B was the answer option given here. So this is the answer. This is the final, this is the steady state value of the velocity of rod. So if you have reached up to this end of this video, thank you for watching the whole video, and I hope that you have enjoyed learning the method of solving this question. Please like the video and also please subscribe my channel. This is the link of my channel. Thank you.